What's up everyone, today we're going to talk about reachable set and confinement sets, and we have some idea about reachability and then reachable sets, but this is something new for us, and of course they're kind of connected, and we will be discussing that in this video. Will be the second video in this playlist where we will be talking about the conditions for like convex Lyapunov functions to determine the stability of a given dynamical system. And let's start with the first definition. Reachable set definition is, I'm assuming this will be like a short video, so system description. Consider a control system described by the differential equation. This is the system where we have inputs, right? And we have initial condition. All right. And this is states. This is the control inputs, right? Where the control signal takes values from the set of admissible control, like some U sets, right? Which also in and of itself needs to satisfy some type of properties, but hopefully in the future we will be discussing like more details. But you can just consider as like nice signals, right? Yeah, not like weird signals. Okay, and that was like a very mathematical description, like the proper description: nice signals and weird signals. Okay, so check Terence Tao analysis book. You will see that. Okay, this is the function that tells us the, informs us about the dynamics. And okay, this was the plant plus the input and the reachable set definition, or rather, wait a sec, yeah, the reachable set at time t here, which takes positive values, and from an initial state. Okay, so there are a couple of variations of reachable sets descriptions, and then we will discuss like the first one. This is, we have like two arguments. One is like time, and the other one is like the initial condition, or like the starting point. And so we have, let's say this is our starting point, and then capital T is the time, and there's some type of input signals that we can apply, and as a result of that, maybe we can only apply, and then this is like a scalar system, for example, maybe we can only apply let's say t is like 0 to 1 second, and from 0 to, I don't know, 10 volt maybe. This is like, yeah, as input it takes like some voltage, for example. And if that is the case, for this specific initial condition, you look at, maybe this is what we will have. This will be the reachable set, for example, right? But here in this case, this, like we have the t, and then we have the initial point. So for this point, we will have a set. Okay, and also notice like there's a distinction. This is you have a bunch of like input signals, and then you will apply these signals to the system, and then you will look at the like states, and get the final points, and then map it to the, let's say x1, x2, map it to the state space, right? Okay, not all the points you will map and then state as the reachable sets. Okay, just the final part, the final points. These are all like, I'm basically looking at states, right? Why I mention that? Because this is one definition, and there are two other definitions, or rather not like definitions, there are two other versions of reachable sets. So here we have a given time and then initial point. Okay, but not interval, like given time. Okay, we are looking at the end of time, right? Not like the whole interval. Okay, so this is like a distinction that we will need to keep that in mind. And let's eliminate that part, and then yeah, now that we have this template definition in our toolbox, so this is, I mean, it will be like a simple thing from now on. So we had the time, and then initial point. Okay, however, here we have time interval, right? So we will look at, I mean, it would be kind of not cool for me to do that, but let's say, imagine that I was able to like dissect it infinitely many points, and let's say T1. So this is a set, right? And T2, and then T. And T1 is like 0 maybe. Okay, and then the T is the T that we have, and there are infinitely many sets. So we are uncountably infinitely many, in fact. So we are taking the union and returning that set. Okay, all those reachable sets, we are taking the union, and then we are looking at the sets. So this was a kind of a messy explanation, but after the template definition, it should be kind of clear what I'm talking about here. And we have one more definition that is related to that. So here, let me get another color just for the fun of it. Here we have the time interval, and then we have the point, and here we have again almost like a point, like some t, not like time interval, some t, and we have a set of initial points, right? And so we discuss what that is, and we are basically doing the same thing for the second argument, and the logic is the same basically, right? We have many reachable sets, and then we are taking union of them, right? So for example, I mean, imagine I was able to like indicate infinitely many points here in this set of initial conditions, and for this I was a, and then for this I got this set, for this I get this set, and then for this I get this set, and imagine that I was able to like do it like infinitely many times, and I'm taking union of them, right? And then this is what we have here. So again, after the template definition, that was kind of, yeah, straightforward. So if you can imagine, we can also do the same thing. And now I am kind of mad because there is a typo, which is really annoying. I just noticed. So we have time interval, and we have set of initial conditions, right? And we are basically like using those two definitions and arriving at a reachable set definition that is not only looking at the points, initial condition points, or the time. We are looking at a duration plus sets. Okay. Now, okay, this was the reachable set definition, and now we will look at confinement sets, and this might be the type of thing that okay, these are the sources. So this video, first of all, will be a part of a playlist, probably the second video, and the video after that one is related to the convex open functions, and then there's something that we will look at, a lemma, and I think it was, yeah, that from this based on this paper, and that paper has a lemma that discusses when you can find a convex open function for a given dynamic system and when you cannot find a convex open function. So like very fundamental, I would say, and these definitions are kind of I don't know, prime you to get the feeling of this lemma that comes from this source. Okay, this is also another paper. Yeah, he's using some of the ideas that this paper is mentioning. And okay, confinement set, so reachable set over time interval. Oh my god, again, one more. Yeah, one more typo. Just delete that, like instead of Euclid set, confinement set. Anyway, and stuff happens, boys. Alright, that's, yeah. This is how we know that, yeah, I'm real. This is not fake. Okay, given a system, so we have dynamic system and set of initial conditions and a time, we have this confinement set be the set of reachable points of solutions of the system. Here, this is like the critical part, after time t. So we, in the previous parts, we discussed that we have that type of reachable set definition, and here this confinement set is the type of thing that is not looking at that, is looking at what would happen after that, rather from t to infinity. Right? Like if you were to draw, okay, you draw something like this, I'm assuming. Okay, what do we mean by that? Let's imagine. Okay, this is, let's look at only 1 point, and 0 to t, okay, and this is the reachable set, for example, right, from 0 to t, okay, and then after that, maybe it will go towards this. Wait a sec, this should be, I'm thinking, maybe it is like going like that, and so I better get another color. Maybe it will be something like this. Okay, because it should also cover that, and this will be, or maybe, and let's look at the 2t, for example, confinement set. Maybe this is a stable system, then after 2t, this is what you have from 0 to t, and then this is what you have from 2t to infinity. Maybe this is a stable system, and then it goes here, and then converge to this set around the equilibrium points. Okay. I'm almost sure that this was not a great explanation, and for some reason my eraser is not, yeah, working, but alright. Let me eliminate that part too. Alright, let's look at the mathematical description of the confinement set, and here the set of states, alright, such that basically generated by this dynamic system, and each initial point takes the value from the given set of initial conditions, and then we have after t, right? That's it. For example, okay, again, these are the sources. For example, oh, we don't have it. Yeah, you can, like we discussed before, let's say this is the set of initial conditions, right? And then we say that, let's look at 10, like 10 seconds, for example, and let's look at, this is the set. for example, imagine this is a stable system, x1 and x2. This can very well be a, so I should get, yeah, this is a point, right? Like equilibrium points. Let's imagine this is a stable system, and in 5 seconds, each of those points converge to equilibrium points, right? Let's imagine that's the case, and then this is like exponential stable, or yeah, finite, maybe even like finite stability or something. The system that we're looking at has that property. Imagine that, and this can very well be that type of set if we have that type of stability property for a given system, right? And yeah, this can also collapse if the system satisfies some type of stability properties, is what I'm saying. All right, yeah, that was it. And then don't forget to subscribe, and have a nice one. All right, you all.